All right, well, let's talk about pushing a box up a hill. So this is the cartoon you started with, and we're going to do a kinetic analysis of this situation, ultimately leading to running up a hill and coming up with a kinetic answer for why running up a hill is harder than running on level. So let's do our kinetic analysis. What are the steps with a kinetic analysis? Identify forces acting on the object. And I'm going to underline on because that's the important part. Later on, when we deal with the human, we'll be dealing with forces created by the human, but in our kinetic analysis, we identify forces acting on the object. And then we put the, well, it's a couple different ways to go, but you can pick a dimension, what direction you want to deal with, horizontal, vertical, medial, lateral, or in this case, uphill, downhill, side to side, or normal to the surface. And then use Newton's second law. Forces add up all the forces acting on the object in that dimension equals the product of mass of the object times the acceleration of the center of mass in that dimension. All right. So it's that simple. Let's go ahead and go through the problem though. I'll start with a blank piece of paper to be able to write some things out, and I'll try to do a bigger picture so I don't have to squeeze everything in too small. Okay, so here's our hill. And we know we started with the situation with the person pushing on the box. So I'm going to replace the hand with an arrow representing the force vector, of course. I'll call that the push force. What other forces are acting on this object? Other forces, any forces, any push or pull that tends to cause movement, doesn't have to cause movement, but tends to. Well, gravity. Now, when you do your drawing of your kinetic analysis, it's really important to draw things correctly. So in this case, I'm pushing on the box in that direction, so I'm going to push it, or I'm going to draw the arrow in that direction. Gravity is pulling down relative to the surface of the earth, okay? And so this force is perpendicular to this surface. Don't draw gravity in a different direction. Up is positive, okay? Forward is positive. So our global reference frame would really be Y and X, okay? It's a good habit to draw arrows correctly. So gravity. What other forces are acting on the object? Now, in this case, this box is sliding up the hill because we know from the problem that I set up that the object is moving in that direction. Okay, so it is going uphill. It's not sitting still. Because it's going uphill, there's another force pushing on the box, and that's the force due to friction. And I can draw this whatever length I want, but I'm just going to draw it here, and I'll draw it the same length as that one. I think in some of the problems you folks turned in, you may have forgotten to include the friction force pushing back on the object. And we know that. We know that that's pushing against the object to slow the object down from moving upwards. It's opposing the direction of movement. Any other forces acting on the object? Well, I guess we could deal with air resistance, but let's exclude air resistance for now. In dealing with this problem, I don't think we were thinking it's a windy day or not necessarily a big box because I drew my hand. So this is not a very, very big box. So drag force is not going to really come into play here. So we'll be lazy and we'll say no drag force. Okay, and I'll do a little smiley face there because that's sort of, oh, that was a terrible smiley face, but hopefully you get the idea. Okay, that's it. Those are the forces acting on the object. Now we need to pick a dimension. And in this case, I wanted to zero in on moving up the hill. So our dimension is here. Now this is my global reference frame. I really want to use a local reference frame or a reference frame that's relative to the surface of going uphill. So in this case, I'm going to do a local reference frame like this. Perpendicular to the surface is normal. Okay, and so, and even when we're dealing with ground reaction forces on the horizontal, our normal force would be the vertical ground reaction force. The other force is the parallel force, parallel component, which is parallel to the surface. So often we would write F with two lines representing parallel if we're dealing with forces. For normal force, we would just say Fn, or sometimes you would write F perpendicular. Lots of different ways to do that. But our reference frame now is really here. All right, and we might even want to call this, you know, uphill or downhill, just to use more layman type language. All right, but I want to get all my forces either in this direction or in the normal direction. So either parallel or normal. This force is already in the parallel direction. That's fine. This force is already in parallel direction. This one is not in parallel nor normal. So I have to decompose this force vector to this new reference frame. Okay, well, decompose the force vector. We're just going to break it into its components that make up, so now it's our vector math. And it's really important when you do these drawings, especially if you're teaching biomechanics, to draw these correctly. And it takes a little bit of practice when you start doing boxes on ramps and something off of horizontal, off the normal or horizontal direction that we're dealing with. The way I remember to do this is I draw a box around the force vector so that the box is, the two corners of the box that are opposite to each other are on the tail and the tip of the force vector. I'll draw it in dotted line to begin with. So here's my box. And those boxes, the box has 90 degrees between each of these lines. It's a rectangle in this case. Graphically, you want to do that step. And you want to practice and make sure you do this right every time, because it just looks good. And so now I want to look at my force component in the normal direction. All I do is I pick one of these sides. Now, the way I'm doing the kinetic analysis, I would draw the force component starting at the origin of the force, at the center of mass of this object. So this is my F normal. This is perpendicular to the surface. All right, perpendicular to the surface. The parallel component is then this side. And we do F, two vertical lines. That's a terrible arrow, but hopefully you see it. So parallel component, reference frame. Normal component, reference frame. Normal is perpendicular to the surface at 90 degrees. Parallel component is obviously parallel with the surface. All right, so once I break this force vector into these two components, I no longer concern myself with this force vector. I'm only going to concern myself with the two components. So you can't have it both ways. You can't, we don't have three forces here. We have one resultant force and two component forces. In our kinetic analysis, we're only going to use the component force because we're going to do one dimension at a time. So that's next. So step one of kinetic analysis, identify all the forces acting on the object. The push force, gravity force, friction force. Step two, pick a direction. In this case, we've got parallel normal, local reference frames, what we're dealing with. And then we have to decompose this force vector into the parallel component and the normal component. Step three, put these forces into Newton's second law. Let's get another piece of paper. Let's do that. So let's start with the normal. This isn't really the one direction we wanted to deal with, but that's okay. It's good practice just to do it. So Newton's second law, we add up all the forces acting on the object in the normal direction. Sorry, let me try to write in the correct direction here. Equals mass of the object times the acceleration of the center of mass in, oh, I forgot a force. And I already realized I forgot the force right when I started writing this, because what I was about to say was there's no acceleration in the normal direction because there's no change in velocity in the normal direction, because velocity of the center mass is 0 in the normal direction. But I only drew one force here. Now I'm going to mess up my drawing, because the force I forgot to include was the other component. This here is technically part of the ground reaction force. This is the ground reaction force. The other ground reaction force would be, now I'm really upset with myself, because now I gotta draw a force vector off that arrow, and I would like to draw it right under the center mass as well, because I got a pretty uniform box, but that's all right. I'll draw it here. And I'm going to draw the length of this force graphically to be the same length as that force. Why? Because I know there's no acceleration in the normal direction, okay? In the normal direction. That is, this box is not moving up and down in this direction. Therefore, the velocity in this direction is not changing, it's 0. And because it's not changing, acceleration is 0. And so I know that this force here, ground reaction force in the normal dimension, is going to be equal in magnitude to that one, because I know the next step is to add up these forces to get mass times acceleration. And I could have done G sub n, but yeah, I'm making a couple of lazy mistakes. Okay, so back to, let's see, I should just start over, but I won't. So back to what I was saying before, we identify all the forces acting on the object, the push force, gravity, the force of friction pushing back on here, which is a ground reaction force, and the normal ground reaction force pushing on the box. Now I could have drawn a resultant ground reaction force and then broken that into the normal and the parallel components as well. But I didn't. I started with identifying at least a friction force and then forgetting to add in the ground reaction force normal component. All right. Hope I didn't mess up too much and you're following along. Okay, so now, and this is why it's good to do this, do these steps, is because we do need to be careful when we're doing our directions. Okay, so now we put our forces into these, we put our dimension down that we're interested in, put our equation down. Now let's put in the forces acting on the object in the normal direction, and up is positive. So I'll still use up from my reference frame here, this is still positive. And oh, I drew that arrow the wrong way, but that's okay. I'm going to still say uphill is positive too. All right, so now I'm going to do Fn, which is due to gravity. I'm going to make that a negative force, plus Fgrf in the normal direction. I'm going to make that positive because that's pointing upwards relative to the surface, equals MaCom in the normal direction. That's my equation. That's my equation of motion. That's my Newton's second law. If I add up the forces acting on the object, and again, this is from gravity, that's the component of gravity acting in the normal direction, plus the ground reaction force in the normal direction equals the product of these two. Because, now don't get confused with, this box is moving up relative to our global reference frame, but it's not moving upwards relative to this surface. This surface is here, and that box is just moving right along at the same height relative to the surface. Therefore, there's no change in velocity, no change in normal velocity. And again, normal is a direction. Therefore, acceleration normal equals 0 meters per second squared. And that's why I caught myself here, is because now I knew if I didn't have another force in here, I would have had one force and I would have had some acceleration, but they're going to add up to 0 because that box is not moving relative to the surface of the ramp. And therefore, ground reaction force normal is equal to the normal component of gravity. Okay. That is not Newton's third law. That is not. We're dealing, right now, we're only dealing with forces acting on the object. Okay? All right, so that's the normal direction, which we weren't really interested in. But doing that actually helped me avoid the mistake of forgetting that pesky little force. All right, so let's do the other direction, which is the parallel direction, which is the direction that we ultimately are interested in because we're going to be talking about running uphill. All right, so now what forces are acting on the object in the parallel direction? So sum of forces in the parallel direction equals mass of the object times acceleration of the center mass in the parallel direction. Now this is going to be fun to talk about when we start doing running. All right, well, let's look at our equations, or excuse me, our schematic here. I've got a parallel force here, I've got a parallel force here, and I've got a parallel force here. I've got 3 parallel forces. We're going to say this direction is positive, okay? Even though I drew my reference frame like that. So we're going to say going uphill is positive. So any force that's pointing uphill is going to be positive. So I'm going to put F push is a positive force, plus F parallel, which is going to be a negative force because that's pointing downhill, and plus F friction, which is also a ground reaction force. It's just a special name, and that's a negative because that's pointing downhill, equals MaCom parallel. Or we can just write it, make it a little cleaner here. F push minus F parallel minus F friction. MaCom parallel. Remember, this is component of gravity. It is not the weight of the object. This component is a function of, and I saw your answers, it's a function of how steep that hill is, okay? How steep that hill is. The steeper the hill, the greater this parallel component. In fact, if I make that hill perfectly perpendicular, then the force of gravity and the parallel component will be the same. If I take this hill and I make it smaller to 0, then the normal force and the force due to gravity pulling down on the object are equal to each other. Okay, so these two components will vary as this hill gets steeper. But now here's my equation for parallel movement. So now the question is, are we speeding up? Are we slowing down? Is velocity constant? Well, now we just need to do the math, and we would need to know some of these numbers to be able to figure out what actually is happening to acceleration in the parallel direction. This component is going to be constant as long as the hill is steepness is constant. This will vary based upon our understanding of how friction of a sliding object varies. We should do another instructional video on friction, both static, where the object's not moving, and dynamic or kinetic friction. All right, but these are our equations, and now we just need to figure out how much the person's pushing, and maybe this is really what we're interested in, is how much the person's pushing. But then we would just rearrange this equation so that all the parameters are on the right side of the equality sign. So we could do F push equals MA/COM parallel plus the gravity component in the parallel direction plus the force due to friction. All right, so that's our box problem. Now I have not gotten to running, and I'm not going to do running in the same video. I think maybe we'll pick up with running, and what I'd like to do is estimate or sketch the anterior posterior ground reaction force component. If we put a force platform on the hill, on the surface of the hill, what would that ground reaction force look like? And our kinetic equation is going to look a little different because running uphill, the foot is not sliding. Okay, so there is no friction force. All right, yes, there is friction, but that allows us to have what we would now call the anterior posterior ground reaction force. And but the foot is not sliding. And so that's going to be important. And so I think in your notes, you already identified that ground reaction force in the parallel direction may be negative, it may be positive. And we're going to have to look at that in a little bit more detail. All right, but that's the kinetic analysis of a box being pushed uphill. Okay, hope that helps. Thank you.